So it's a pleasure to welcome Daniel Cho from Yonsei University, who will be speaking to us, introducing symplectic homology and its applications.
Thank you for the introduction and thank you for the opportunity to participate in this wonderful workshop. And let me start explaining about my favorite symplectic structure is a certain non-complex symplectic manifold, but it's simple, so it is a kind of compilation of certain complex symplectic manifold with boundary. And the special structure is its symplectic two form is exact. So exact means there is one form, and our symplectic two form is D of that differential one form. And then there is a vector field with satisfy we differentiate symplectic two form along the vector field. It preserves our symplectic two form, and the vector field is called Rubel vector field, and it's transversely pointing outward along the boundary. And the boundary has a complex structure. This one from alpha restrict to boundary give a contact force, and the Rubel vector field like a transpose and restrict to tangent space of the boundary give a contact structure on the boundary. And for example, like consider a complex plane D and consider polar coordinate R and theta, and consider one form alpha is R squared is theta, and our symplectic two form B alpha is R d theta. And let's find the Rubel vector field like a set is we plug in the alpha that give us alpha. So our Rubel vector field is on half R dr, like it's on the unit disk on like a complex plane. It's a unit disk with this Rubel vector field give us a compact symplectic manifold with boundary, and we call it Rubel domain. And I'm considering like using a Rubel vector field. I want to build up a symplectic manifold, so I will draw like my Rubel domain, like starting point is bottom and build up like and compilation of Rubel domain is along the contact boundary. Consider contact boundary times positive real line, and extend our contact form using simplification. So we extend like a symplectic form, and so that like our flow of Rubel vector field defined at any time. So it's a compilation like of the Rubel domain, and the picture is like this, very simple. And so the one of my favorite example is affine variety, which is a set of solution of polynomial equation, and we consider affine. We can see affine variety as a Rubel compilation of Rubel domain, like a two-way, but they are equivalent actually. Consider is as a affine variety embedded in C to the n as a embedded. Consider like as previous example, like consider like a polar coordinate and take a large radius for center origin and intersect with our affine variety. Then the intersection and induced like R dr d theta, the form, and the f function like give us Rubel domain structure, or we consider affine variety as a complement, like consider projective variety first and complement of simple homomorphism divisor, empty divisor, and the divisor we consider like a line bundle with zero vector is corresponding to that divisor, And consider norm on the line bounded and take a norm of section and minus log of that normal section function give us a G, and considering this G is actually like a pluralismal harmonic function, and this using this function we get a two-form like take a minus dd like a c means j prefix of the differential and g, and this two-form and the corresponding Rubik vector field gave us Rubik domain, completion of Rubik domain structure on affine variety. And
So what's the unit vector field in this example?
Rubik vector field is like we have a pluralistic harmonic function like a f over g, like a previous, and take a gradient, kind of gradient like a vector field or long pluralistic harmonic function, and that give us Rubik vector field. And this is a very small class of completion of Rubik domain. Affine variety is a very special like small class. But I mean, so we have a non-compact symplectic manifold. It's a completion of compact boundary with a Rubik vector field, and we consider one more vector field, Hamiltonian vector field. Is defined by a Hamiltonian function. Actually, Hamiltonian function on our manifold is I don't have a. This is almost zero inside of a compact part, and become let's consider linear like when we go this x-axis is r direction, like r direction means the positive real line direction, like a cylindrical like a direction. Like we consider like a family of Hamiltonian function like almost zero, but it increases along the cylindrical ends, and consider it as my image. It's not my personal thing is I consider Hamiltonian function is a temperature. The temperature is inside almost freezing, and when you go out and the temperature go up like so. Then then Hamiltonian vector field is so which we have a Hamiltonian function and we differentiate. We have a one form EH plus minus EH, and our symplectic two form is non-degenerate, so we get a one vector field corresponding to Hamiltonian function. So we differentiate one form, and our symplectic two form is non-degenerate, so we get a Hamiltonian vector field. And consider like a one periodic orbit along the Hamiltonian vector field. Like for example, like I draw r direction like the y-axis, and inside of Rubik domain compact part is a zero, so the vector field actually like a zero, like a constant, and a little bit apart, so it's discrete, like zero. And then like when the temperature go up, the Hamiltonian like move move and generate Hamiltonian orbits, on periodic Hamiltonian orbits. Some orbits are constant, some orbits are non-constant. And actually like others ask this conjecture like that consider like a Hamiltonian symmetric homomorphism coming from Hamiltonian vector field, and consider fixed point. Fixed point corresponds to periodic orbit, right? Like a fixed point. The minimum number of fixed point of Hamiltonian symmetric homomorphism, the level restriction isotopic to identity, that kind of thing. The minimum number of fixed point is bounded below by the sum of Betti numbers. Yeah. So it's a kind of for me the question is more like dynamical, like a behavior is bounded by topological thing, and the flow answer using by build up of flow cohomology. The idea is generators are fixed point, right? and the generators of the fixed point, and there's a differential map. So we kill differential, and the Becky numbers are less than generators. So that's the idea. But the amazing part is this theory, like a flow homology, is built on that era's breakthrough work. Like for example, like understanding a moduli space of Riemann surfaces, like telling one for the compactification of the first, and maybe Koenig-Gender. I think I thought alphabetically, but I put like Koenig-Gender index is actually the generator have a well-defined index, and Gromov developed general morphics, like a moduli of general morphic Hall theory, and the H principle that time, and also Donaldson and House, Uhlenbeck, and study like a more like a understanding on like a moduli space analytically, and like a perfect complete vision. I'm not expert on that, but and we can have an insight from PQFT and kind of also like mathematical physics idea. And the thing is, important idea is we want to do worse theory, not just on the points, but any geometric object. So Hamiltonian flow homology is roughly like consider loops on simplicity manifold and do Morse theory. Then the corresponding height function is the symplectic action function over Hamiltonian action function is each loop has we have when we integrate along the loop, and we evaluate along Hamiltonian function, then that give us a loop height function on the loop space. And the critical elements means so this is a calculus. We have a function and we differentiate like a f prime is zero, and we find a local minimum, maximum, and critical elements are exactly look at this this part is critical elements are integral curve of Hamiltonian vector field, so Hamiltonian orbit. And consider on the space of loops, consider L2 metric coming from integration. Then the corresponding negative gradient line is consider loop, critical two loops, and the gradient line just imagine that it should be like a cylinder connecting two loops. So but we need to solve the equation. So plug in negative gradient equation. Then here we computed here previously here, right? Then the amazing thing is there is we have omega symplectic form, and the Riemannian there is a omega. We will consider a symplectic form is there is a space of almost complex structure J, and we choose J is omega compatible, means we plug in actually omega J that gave us Riemannian metric compatible. We have a symplectic structure, almost complex structure, and Riemannian metric is compatible. So, and such a almost complex structure are profound, and the modular space is contractible, and that is a Gromov ground-breaking result. And that, so such a kind of theory is used to develop a Gromov-Witten invariance, around that time. And so we get omega, G, and J. So we compare here, gradient. Negative gradient line is some cylinder from R times S1 to our symplectic manifold satisfying this equation. Compare this part. And this means, here, this part explain, consider this part is a Cauchy-Riemann equation. And we we have a like gradient flow line, actually like a Cauchy-Riemann solution of Cauchy-Riemann equation, a little bit perturbed by data of Hamiltonian. Like and the picture is when you compute the calculus and the picture is this. So the loop space consider height function, critical elements are Hamiltonian orbit, right? Like constant, some non-constant, and gradient flow trajectory, like a perturbed Cauchy-Riemann equation, like a pseudo-hologram cylinder connecting two orbits, and then we can define like a Hamiltonian flow homology given like a Hamiltonian function. We consider like a generator and differential. But this data depends on choice of Hamiltonian. But we consider like a sequence. We consider like a sequence of Hamiltonian, like your direction. We chose almost zero and go up, almost, and a little bit bigger for almost zero and go up. And eventually, we consider increasing sequence of Hamiltonian function, eventually going to zero and infinity. Zero inside of reveal domain and the cylindrical energy of problems infinity. Then, and each Hamiltonian we have sequence of Hamiltonian. We construct the homotopy and construct a chain map between them and take we construct the direct system of Hamiltonian homology and take a direct limit. And the one important thing is actually when we consider this to get a nice chain map, the thing is we need a maximum principal sum part because we have a non-compact symplectic manifold. So even like to orbit, the cylinder might go like infinity like this, but the maximum principal like constrain the cylinder the gradient trajectory, so we can define the chain map and chain map so get direct limit. So we get symplectic homology is a direct limit of Hamiltonian flow homology that is not depend on choice of family of Hamiltonian. And then there is a interesting long sequence coming from action calculation. So we define like our height function is action function, right? And there is a very small action, almost zero, like very small epsilon. We have a long inject sequence from very small action part and whole part and a positive action part. And the very small part is actually isomorphic to a singular homology of our manifold. And then we have a long inject sequence connecting like a positive. This is a positive part of symplectic homology connecting constant orbit, like our singular homology or Morse homology of our manifold. So this connecting delta map is explain this piece, connecting non-constant orbit to constant orbit. So I was interested in studying some property, studying bidirectional geometry using symplectic homology or symplectic geometry, following my thesis of Margalit-Winarski. And then I found that many interesting already done, and I just thinking about is there anything left, and I found that there is a very interesting property of given algebraic variety or projective or affine is so projective variety is uniruled if generic point at every point there is a projective line CP1 passing through that point every point this is a uniruled. Affine variety is C uniruled if every point there's a complex line C passing through the point like that. So this is people bidirectional geometry. People want to classify some variety of two bidirectional multiplism. And one of the classification is consider Fano, Calabi-Yau, or general time. And a Fano is rationally connected. Every 2 points connected by a line, a very strong property. And the weaker property may be uniroot, rather than rationally connected. And for me, a uniroot is locus. Uniroot maybe consider we cannot determine uniroot whole side is uniroot, but some part is uniroot because I feel that's meaningful because every block locus is a uniroot, definition. So I want, and we have a line actually, using from the delta, the line. So the main theorem of my thesis is some symplectic criteria on uniroot subvariety, detecting uniroot subvariety of affine variety using symplectic homology. So consider we have here is a delta map from long-eject sequence, and consider we have a homologous flat here, and if there is the degree is important m, and there is an image of the connected delta map, then we saw there is a non-constant actually map, a perturbed Cauchy-Riemann equation solution, and then there is some uniroot subvariety of given affine variety complex dimension at least n minus k. So this is the idea is a very low idea. We propose that a Cauchy-Riemann equation, perturb Cauchy-Riemann equation to genuine Cauchy-Riemann equation, and then there is a holomorphic curve, but the making a rational curve. We do some degeneration to the normal curve, a family of symplectic manifolds, and we the limit is break, and the one piece become inside of the projective variety and attach with the device. So we degenerate our holomorphic curve into rational curve. And then the interesting is when we degenerate, sorry, can you when we degenerate the constant orbit part, actually that trajectory is the holomorphic curve. When we degenerate, it intersects with most descending chain, and we have a rational curve, and we have that means that we have a family of rational curve, a certain dimension to intersect with the most descending chain. So the dimension coming from that condition. And so given affine variety, I can if I can compute symplectic homology and long-eject sequence, I can detect some uniroot subvariety, some a union of uniroot subvariety, considering image of delta. And I don't have much time, so I have some criterion how deep we can get a uniroot locus, but so this is coming from the direct corollary of proven properties, and we can handle a patch for example, a simple example is symplectic Weinstein manifold has a subcritical handle, and Chelibach showed that subcritical handle does not change the symplectic homology. So the side part is isomorphic, but if the handle attached change the homology, then we get a uniroot subvariety, from delta, non-trivial delta. Then I have I have one application is so there is something pretty interesting, like a cylindrical affine variety, which is defined as a affine variety till some like a hypersurface, then it becomes a 3 times another affine variety. It's a quite simple, very strong condition. So cylindrical affine variety with delay hypersurface and becomes 3 times n. Then using Quen's, there is a symplectic homology Quen's formula. Then the deleted part symplectic homology is 0. So my question was, how about the original like affine variety? Is if we delete then symplectic homology 0, then how about the symplectic homology of the original manifold, original variety? Then I think I got some spectral sequence. This is a spectral sequence coming from deleted part to converge it to non-deleted part. This is a work like I used like homomorphism relative symplectic homology and the Meyer-Baker sequence and some H principle and the combination of things. But the main idea is actually even we delete the hypersurface. Hypersurface are quite like a very strong condition. So even we delete hypersurface, generators of two homology are same. But the differential we consider different. Like we cannot pass through the hypersurface, right? So actually that is coming from counting like intersection of differential map with the hypersurface and or winding number, like a winding number won't change. So the filtration for the spectral sequence is coming from that. And yeah, any questions? And I have a more like application of this spectral sequence using bidirectional map. One bidirectional map for affine threefold. This spectral sequence only works for complex dimension at least 3. It does not for complex dimensions because of H principle cannot work. And so like but I think I don't have, but if you're interested, I can explain this part later. But I think I like this part because I plan to introduce the symplectic homology to people here, and I learned very interesting like a math from you guys. So maybe this part I'm not the expert, but I just quote some result. So Viterbo showed that the symplectic homology of cotangent bundle of compact Riemann manifold is actually homology of the free loop space. And for the people who like Hochschild homology, symplectic homology is actually considered wrapped to category and take a Hochschild homology and give us symplectic homology. And if someone interested in like computation example, Pascal have like some like using tropicalization and some zeta function and mirror computed some symplectic homology of low Calabi surfaces. And if anyone like a causal duality, there is a causal duality between. So we have what is a Lagrangian here inside it? Consider like we have a Liouville vector field, Liouville flow, but the time back we consider minus infinity time, like flow down, then we have a skeleton. Like there is a Lagrangian skeleton or Lagrangian what is it? Like a Lagrangian skeleton. The example is consider Riemann surface is a Lagrangian skeleton. We consider it ribbon graph inside of punctured Riemann surface, and then the Lagrangian, and there is a like a Legendre in the contact boundary corresponding to the Lagrangian, and the economic likely show that certain DGA from Legendre and the Lagrangian flow is a causal of Hamiltonian flow homology of Lagrangian causal dual. They said it's a generalization of kind of homology complex of base loop space and like a cohomology of that space. And the spectral sequence I constructed is inspired by Birman-Hilden and MacLachlan-Harvey's spectral sequence. They show that quantum cohomology, they construct spectral sequence coming from symplectic cohomology deleted divisor to quantum cohomology of projective variety. So they construct some spectral sequence and show quantum cohomology as a deformation of symplectic cohomology. And the last part, someone who like opera is I don't know what does that mean, but I just thought outside Birman recently showed that they construct some framed into opera acting on Hamiltonian flow theory and show that relative symplectic cohomology, relative is some restricted part, together may be a third sequence. Relative symplectic cohomology carry natural Bartolini-Bisky algebra structure. So hopefully that inspire you some more work related to symplectic geometry. Yeah, that's it. Thank you.
Very much. Questions?
Is there any suggestion as to why the small part of this symplectic homology that's marked as singular homology? So on that, I guess on the next slide.
Yes.
Yeah, bottom left. Is there any suggestion for that ice modeling?
There is you can define let me this part is there is some perturbation Hamiltonian vector becomes zero, then that function become a real Morse function on the manifold. So it's roughly speaking, but it's a really Morse critical point in the gradient trajectory inside. When you a Hamiltonian is almost zero, then they become a regular, the original Morse homology inside. Yeah.
Your result regarding this universal subvariety, I don't know anything about. Can you abstract such an existence of universal subvarieties, or are you?
I mean, the function is very strong. If I compute the long inject sequence and look at the delta map, if the homological class is the image of delta map, then I can detect universal subvariety. But the more practical thing is this diagram. So some people Katzers and Murphy, they construct a Legendrian front projection diagram. Compute the from given they have some example given affine variety, they draw some Legendrian front diagram. So compute a handle, completely understand the handle of patching, and then if the in their diagram, if they can detect some subcritical handle given affine variety, then I can see the universal subvariety, but it's a theoretical. I didn't do any computation yet.
No further questions. Thank you, speaker again.